Okay, let's just dive right into this. Welcome to today's Explainer, where we're going to unpack what is honestly a genuinely fascinating scientific detective story. When we think about predicting geological threats, we usually picture those massive seismographs, right? With the needles jumping wildly all over the paper. But what if I told you that to uncover some of our planet's most hidden, most dangerous tectonic stresses, geologists aren't just looking at the Earth anymore. They're literally listening to rocks cracking. It sounds wild, I know. But today, we're exploring a groundbreaking study by Das and colleagues from the Journal of Geodynamics. And they use this revolutionary technology to hear the Earth's floorboards squeaking long before they snap.
So, here's our roadmap for today. Number 1, we'll establish India's active fault line. 2, the stress measurement problem. 3, listening to rocks crack. 4, the Angel M field study. And finally, number 5, local versus regional stress.
All right, Section 1, India's active fault line, the ancient scar of the Narmada-Son lineament. To really understand this breakthrough, we've got to understand the stakes first. And the stakes here, they're incredibly high. We're looking at a massive geological feature in peninsular India, known as the Narmada-Son lineament, or just the NSL. Now, this is an ancient rift zone. It's basically a scar on the Earth dating all the way back to Precambrian times. But just because it's ancient doesn't mean it's quiet. It is dangerously active. If you take a look at the dotted green ellipse on this map, you'll see our primary field area stretching about 600 kilometers across central India. See those dots and stars scattered all around it? Those are epicenters of moderate to high magnitude earthquakes. This ancient rift has repeatedly proven it's still very much alive, producing catastrophic events like the 1997 Jabalpur earthquake, which hit a magnitude of 6.0. So the Earth here is under immense pressure. Moving on to Section 2. The stress measurement problem. Why gathering tectonic data is usually so frustrating.
Here's the core mystery geologists are facing. We know the NSL fault is active, right? But figuring out exactly which direction the tectonic stress is building up has traditionally been, well, incredibly difficult. We desperately need this data to understand seismic hazards, but getting it feels a bit like trying to read a book with the lights completely turned off. So I want to pose this directly to you. How exactly do you measure stress beneath the surface of the Earth without digging a massive hole? In traditional geology, this is an absolute logistical nightmare. You're essentially forced to rely on sheer dumb luck. You basically have to wait for a dangerous earthquake to happen so you can study the fault plane in the aftermath, or you have to spend an absolute fortune.
Let's look at the stark contrast here. The traditional methods? They're expensive and they're sparse. Like I said, you're either waiting for a disaster to strike or you're out there drilling 800-meter deep boreholes just to measure hydrofractures. That's exactly what they had to do in the Malunj-Kolland area. And that leaves us with a really non-uniform, highly fragmented picture of the world's stress map. But over on the right, we have the hero of our explainer today, the geogenic electromagnetic radiation, or EMR method. This technique is cheap, it's quick, it's totally portable, and crucially, it allows researchers to acquire stress data almost anywhere they can physically place their equipment. It's a total game changer.
Which brings us to Section 3, listening to rocks crack, the science of fracture-induced electromagnetic radiation. So how does this actually work in practice? Well, we're basically using a new technological magnifying glass. We're tuning into the microscopic squeaks and groans of the Earth's crust. Long before a macro earthquake actually hits, the Earth gives off these tiny warning signs. And if you know how to listen, you can map out the invisible forces at play. Let's walk through how this builds step by step using the Reach's Luckner model. Okay, step 1, strain incrementally increases in the Earth's crust. As that pressure builds, we hit step 2, where microscopic cracks, we're talking nanocracks here, begin to nucleate at tiny flaws in the rock. Now step 3, this is where the physics gets really beautiful. As these cracks form, physical chemical bonds are literally being ripped apart, tearing positive and negative ions away from their equilibrium states. And finally, step 4, these oppositely charged ions desperately try to reestablish stability. They oscillate, they vibrate, and as they do, they emit tiny, high-frequency pulses of electromagnetic radiation. We aren't feeling the ground shake? Actually, scratch that. We're detecting the microscopic electrical sparks of rocks literally crying out under pressure.
All right, Section 4, the Angel M field study. 18 locations, 600 kilometers, one crucial signal.
Now, theory is great, but Das and the team needed to prove this actually worked across a massive scale. So they took this EMR theory out of the lab and into the real world, surveying a staggering 600-kilometer stretch of the Narmada Sun lineament across 18 distinct locations to map out those hidden tectonic stresses. I absolutely love this image because it humanizes what is frankly highly abstract science. Here are the researchers out in the field in central India. That device they're working with, that's the Angel M, manufactured in Russia. It's incredibly portable. They place the receiving antenna directly on the rock surface, align it very carefully, and then take measurements at 5-degree intervals, completing a full 360-degree rotation. They are literally sweeping the rock to find the exact direction where those microscopic electrical signals are the absolute loudest.
But take a look at the sheer scale of the noise they had to filter out. The blue bars you see here represent anthropogenic or human-made electromagnetic radiation. It's massive, it's loud, and it forms this very predictable sinusoidal wave. Now look at those tiny red bars down at the very bottom. That right there is the true natural fracture-induced EMR from the Earth. It's quiet, it's subtle, and it's highly irregular. The Angel M device has to use high-pass analog filters to basically ignore our human static and isolate the true voice of the cracking crust beneath us.
This leads us to Section 5, Local versus Regional Stress, the twist discovery. So after filtering out all that noise and mapping the signals across 600 kilometers, the researchers compiled their data. And what the Angel M device heard in the field, it completely contradicted what geologists expected to find based on the massive regional forces acting on the Indian subcontinent. The crucial takeaway is this exact number, north 85 degrees east. That is the newly discovered mean azimuth, or direction, of the maximum horizontal stress acting right along the fault line. And 85 degrees E is effectively an east-west orientation. And to a geologist, that number is a massive, massive plot twist. Let me explain why. We basically have a clash of titans going on here. On the left, we have the regional stress. The entire Indian plate is smashing into the Eurasian plate, which is what created the Himalayas. That massive, ongoing collision pushes the continent in a north-south orientation. Geologists naturally expected the stress along the fault to reflect this massive continental crash. But on the right, the EMR method revealed that the local stress along the Narmada Sun lineament is oriented east-west. So, despite the continent-crushing forces of the Himalayas to the north, the local environment right near the active fault is entirely writing its own tectonic rules. It's wild.
So let's summarize exactly what this means and why this is so absolutely crucial for us. First, stress orientation just isn't uniform. It changes significantly at shallower depths, roughly around the top of 1,000 meters of the crust. Second, local faults are incredibly powerful. They can warp and modify the stress field completely away from those regional continental norms. Third, the researchers proved this by showing how the stress aligned perfectly east-west right along the strike of the Narmada River and the fault itself. And finally, as you move further away from the active fault zone, the Earth's stress field obediently returns to the regional north-south direction of the Himalayan collision. Mapping these highly localized, hidden stress bubbles is just an absolute game changer for understanding active faults and properly preparing for localized earthquake hazards. I want to leave you with this final thought today. If a simple portable antenna can prove that local faults write their own tectonic rules, completely ignoring the crushing weight of the Himalayas, well, what other hidden stresses are we missing around the globe? What invisible forces are building up right beneath our feet, just waiting for us to stop looking and start listening? Thank you so much for joining me for this explainer. Keep your curiosity sharp, and I'll catch you on the next one.